Hello everyone, we meet again with a topic related to cryptography, and now we will discuss data encryption standard, or DES or DES. Okay, we will start with history. It was actually based on Lucifer cipher. Lucifer cipher was developed by IBM. The team at the moment was led by Faisal, and Lucifer cipher uses 64-bit data blocks with 128-bit keys. Yeah, so since it was led by Faisal, then the cipher was based on Faisal structure. Then Lucifer cipher was developed as commercial cipher with the input from NSA and also other parties. After that, in 1973, there was a call for proposal for national cipher standard by NPS. For the proposal, IBM revised Lucifer. Then it was accepted as TS as the standard. But since it is quite old, then it is not used anymore. Actually, in 1994, NIC already recommended that DS could not be used for encryption of data that is related to classified information. And even in 1999, NIC suggested the use of triple DES to replace DES to improve the security of DES. So triple DES actually is based on DES, but it is executed 3 times. Now we will have a look at the detail of the DES. So DES consists of 3 phases. Actually, the main phase is the second one. The first one and the last one is just kind of permutation. So there are 3 phases here. The initial permutation. Initial permutation is this one. We use a determined table to do this. And then after that, we have 16 rounds. 16 rounds here. 16 rounds. Yeah. Each round we will make use of a key that is derived from the main key. The key here is called the subkey. So we will have K12, K16. After that, the result will be reserved or swapped. And then after the 16 rounds and the swapping process, we will again reverse the sequence of bits, using the inverse of the initial permutation table. So when the first time we do the processing to the plain text, we use initial permutation. The last time here we use the inverse of initial permutation table. So it looks like that we put back the bits into the original positions. And each round here using the same structure as Faisal structure or Faisal cipher here, except that we use permutation here, while in Faisal structure there is no permutation. This one and this one doesn't exist in Faisal structure. Okay. For the tables to do permutation, there are already six tables determined by the standard. The first one is the initial permutation, the one that is used in the initial process. And then the second one is the inverse of the initial permutation, the one that is used in the last phase. And there are 4 other tables: expansion permutation, permutation function, as boxes. These 3 are used in the function, in each function of each round, in a function in each round. And these 2 tables, PC1 and PC2, are used for key scheduling algorithm to derive the subkeys K1 through K16. Okay, this is the initial permutation. So for this one, actually, yeah, we just do permutation to the bits in the plain text. So for example, the second bit in the original plain text now is placed in the, or is positioned in the 8th place. Yeah? And then the first bit in the original plain text now is placed in the 40th place in the current sequence of bits. Okay, so that's how it works. Just do permutation based on this table. And this is the inverse of the initial permutation table. So from the previous table here, the second bit now becomes the 8th bit. In the inverse, it is put back in the original position. So in the 8th bit, here is now placed in the second bit. So it is kind of putting back the bits into their original positions. For each round, we use the phasal structure. So we divide the the sequence of bits into 2 parts: the left parts and the right parts. The left parts consists of 32 bits, and the right parts also consists of 32 bits. And the same as, or similar to phasal structure, for the left part in the next round, then it is obtained from the right part here. Just copy the right part, it will become the next left part of the next round. While for the right part in the next round, then we have to do this operation. So there are actually several operations here. We have to use, or we have to do function f. We have to apply function f to the right part here using the keys, the subkey at the round. Then the result will be sorted with the left part to produce the right part of the next round. So this is the formula. So Li equals to Ri minus 1 because it is just copied, while Ri equals to Li minus 1, this one, sort with Ri minus 1 applied with function f with the key ki. So this one. Yeah, so here the function detail of function f will be discussed later on, but it is actually just doing some processing to the 32 bit of R, and then it will be sorted with 48 bit subkey, and the result should be again a 32-bit to become this one, to be short, to be short with L to obtain RI. For the key processing, we also make use of key scheduling algorithm. So in each round here, we do a kind of left circle shift and permutation operations. The permutation operation is the same, but since we use or we do left circle shift operation, then the subkey will be always different for each round. Yeah, okay, so this is the details of function f here. So in this case, I think I'll just go to the illustration here. So here the input is r. The input for this function is r. So it consists of 32 bits. But we have to store the bits with the subkey. The subkey consists of 48 bits. So what should we do? We need to expand the 32 bits into 48 bits. We use here an expansion table to do the expansion. So from 32 bits, then using expansion table, then we will get 48 bits. Then the bits will be stored with the subkey. This one. Of course, the result will be again 48 bits. But since it must be stored with the left part of the sequence of bits, which consists of 32 bits, then we need to again reduce the 48 bits into 32 bits. This one. So in this case, we have to use S boxes. We group the bits into groups of 8. Yeah. So we will have, group of 6. So we will have 8 groups. For each group, then we use different S box. So for the first group, we use S1. The second group, we use S2, and so on. The result for each group using S box is a 4-bit, group of 4 bit. So we will have 4 times 8, which is 32. And then after we get the 32 bits, we do permutation using table P here, and the result is this one, 32 bits. And this will be stored with the left part of the sequence of bits at that round. And the result of that sort operation is the right part of the next round. Okay, so I hope this is clear. Yeah? So this is the explanation of the function f here that is illustrated in this slide. Yeah, this is the expansion table E. So as you can see here, since we need to produce 48 bits from 32 bits, then we need to repeat several bits here. So as for example here, the first bit appears here and appears here. So the first bit appears in the second bit of the 48, and then it is repeated in the last bit, in the 48 bit. And then this one 4 also appears here, and so on. So there are several bits that appears twice. Okay, and for the S box tables, we make use of S boxes here to reduce 48 bit from 48 bits into 32 bits. The input for each S box here is the 6 bit, and the output is 4 bit. For example here, if the input for S1 here is this one. We will use the first bit and the last bit to indicate the row in the X box. So in this case, since we have this 100001, then the first bit is 1, the last bit is 1, so 1 is 3. Then we will use the third row in the S box. For the column, then we will make use of the bits between the first one and the last one. So it will be 0, 0, 0. 0, 0, 0 is 0. So we will see the 0th column. Okay. Since the element in the third row and the 0th column is F, then the result of this input, or the output of this input, is F. F is 1, 1, 1, 1. So this one again is 4 bit, for a sequence of 4 bit. From 6 bit here, then we will get an output consists of 4 bits. So the same methods are applied to other groups of 6 bits using the corresponding S box. Yeah, and then after we get the 32 bits, we do again permutation to the bits, and this is the table to permutation. So for example, the first bit now becomes the 9th, or now is placed in the main position. For the key scheduling algorithm, we use here two steps. The first step is initialization. Initialization here using 64 bits actually. Yeah, so the original number of bit in the key is 64 bits, but we only make use of 56 bits. Yeah? How we do that? We group the bits into group of 8, and every 8th bit is ignored. Yeah? So we will get 56 bits from 64 bits. Yeah, after that, after we get the 56 bits, then we do permutation to the bits using a table again, which is called PC1. Table is called PC1. So I think, okay. Yeah, this one. This is the table, PC1. Just do a similar permutation to the one that I already explained in the previous slides. For each round, the key scheduling algorithm should produce a subkey. How to do that? We use the 56 bit from the previous round, or maybe from the initialization process in the first round. Then after that, we divide the bits into two, C and G, Ci-1 and Gi-1. Of course, it consists of 28 bit. And then each part is applied with a 1 or 2 bit of circular shift left operation. 1 or 2 here is based on this table. So for the first round, then we do 1 bit circular shift left operation. For the third round, then we do 2 bit of circular shift left operation. Then after that, we do again a permutation using table BC2, and this will be the subkey in that round. While for the next round, we don't need to do permutation using PC2, just using the circle shift left operation. Yeah, this is the illustration. Using this illustration, then it will be more clear, yeah, how to do that. So we get 58 key, 56 bit of key, yeah? And then we use PC1 to do permutation. Then we divide into two, C and T, C0 and T0. Then we do left shift operation, yeah, using the table. After that, we will get C1 and T1, and for these two, then we do permutation using PC2, using PC2. The result will be K1. K1 is the subkey for the first round. But for the subkey for the next round, then from C1 and T1 here, we do again left shift operation using the table, and then the result is C2 and T2, and we do again permutation to C2 and T2 using PC2, and the result is the subkey for the second round, K2. Yeah, that's the way how we do key scheduling algorithm. So I think this is pretty easy. For this one is table PC1 and PC2. Yeah. We already discussed how when we use PC1 and PC2. For the decryption, it is very convenient because actually we use exactly the same algorithm, but the subkeys are reversed. Yeah? So here we have the encryption process from round 1 to round 16. We use K1 to K16, and the output is the ciphertext. For the decryption, we start from the ciphertext. The input is the ciphertext, and we use the same round 1, round 2, and so on. But the subkeys are used in reverse. So we start from K16 here instead of K1. K16, K15, and so on until at the last round 16, we use K1. Okay, and that's how you do decryption. Exactly the same algorithm, but the subkeys are used in reverse. At the time when it was proposed, there are the advantages. One of the advantages of DS is that the key looks like very large. So we have here 56 bit of key. There will be this many values, very large values. So brute force was expected to be difficult. But in 1997, it was proven that it is possible to do brute force analysis to DS. It required several months to do brute force analysis, and in 1998, it required less than 3 days. But if the plain text is not the original text, then even though it is decrypted, then it is still difficult to analyze. So for example, if you first compress a file, and then encrypt it using DS, then if it is broken, the result will be still a compressed file. So if it cannot be recognized, I mean the algorithm for the compression, then of course it cannot be it cannot be revealed. The content of the message cannot be revealed. Okay, but so plain text here is also important, whether it is the original text or a text that has been processed. Yeah, even at the time when it was proposed, people already criticized the use of TS as a standard. The first reason is that the key size is too small for organizations with big resources, and actually Lucifer cipher uses 128 bit of key, so TS uses less than half of the length of the key of Lucifer cipher. And then the next one is the design criteria for the tables is not known, and statistical test shows that the tables are not random. But still, since it was a standard, then for the first 20 years, since it was standardized, there was no evidence that there was an effective way to treat TS. Yeah, okay. This is the source of these slides from Cryptography and Network Security Principles and Practice book by William Stallings. Yeah, I think that's it about TS, Data Encryption Standard. I will see you in the next video about another topic, and thank you for watching.